This video will cover point matching for function generation. So if you want the input and output link of a 4-bar linkage to be related by a linear relationship to match at initial, middle, and final points, then you will use point matching function generation. So these are the key equations here. There's the vector loop position equation, and then there's Freudenstein's equation, which is this big long thing over here with the cosines and the k's. So the k's are actually ratios of the link lengths. So one of the link lengths you'd have to be able to, you just have to choose. And the other link lengths would be able to be calculated because you'll know the theta 2s, you'll know the theta 4s, and so then there are 3 k's to figure out. So those 3 k's, if you get an equation for each of those, you can solve for 3 of the r's. So you have to pick one and then you solve for the other 3. So the 4-bar linkage equations in that form are called Freudenstein's equation. So they determine the relationship between the input, which is theta 2, and the output angle, which is theta 4. So we use that equation as kind of the basis for this function generation. So the procedure, first you want to find the function of interest. Function of beta and gamma, which would be the change in input and change in output. You want those to be related. So then you choose 3 points, initial, middle, and final, in those initial conditions. Where does the linkage actually start at? So then you calculate the input-output points, so the theta 2 and the theta 4, based on the initial positions and then the beta and gamma equations. So once you've got those calculated, that's kind of the basis, and then write the Freudenstein equations for each point. So you'll have one Freudenstein equation for initial, one for middle, one for final, and with those 3 equations, you can solve for the 3 k values. You use matrices to do that easily. And then once you've got those k values, you can solve for the link lengths. So you'll choose one, usually you choose R1 or choose the ground length, and then you can use the k equations to figure out how long do the input, the output, and the coupler need to be. So let's do a specific example of this. So we're going to use the water pouring linkage as an example. So first, let's just put on the normal vectors. So we'll have R1, R2, R3, and R4. So the angles of these, say we put our coordinate frame X, Y. Then when the linkage moves to a new position, so we'll draw the new position in blue. So if this is the new position, then let's label what the angles are. So this is theta 4 initial. This is theta 2 initial. And then this amount that the output link moves is gamma. And this angle that the input link moves through is beta. So step 1 is find the function of beta and gamma. So we want the function that relates the input and output positions. So let's say that is f of beta gamma equals 1/3 beta minus gamma. So that corresponds to gamma equals 1/3 beta. So remember that beta equals theta 2 minus theta 2 initial, and gamma equals theta 4 minus theta 4 initial. If we take the derivatives of these, then we get d beta equals d theta 2 the gamma equals the theta 4. So we'll just take those derivatives right there because we might need them in a bit. So then the next thing we need to do is figure out what 3 points do we want to match. So initial, middle, final matching points. So let's make a chart for that. We'll have theta 2, theta 4, beta, gamma. And initial, middle, final. So let's say we want theta 2 to be 60 degrees, 80 degrees, 130 degrees, and we want theta 4 to start at 55 degrees. So now we have the starting point for theta 2 and theta 4. We got those initials, and we got all of our desired points for theta 2. So now, using the function that gamma equals 1/3 beta, we can calculate beta and gamma and theta 4. So let's fill that in. So over here, beta is theta 2 minus theta 2 initial. So since theta 2 initial is 60, beta for the first point is just going to be 0. Write that down to remember. So 60 minus 60 is 0. So then 80 minus 60 is 20. And 130 minus 60 is 70. So that got beta. Now gamma is 1/3 of beta. So we just divide all the beta column by 3. We'll have 0. 20 divided by 3 is 6.67 degrees. And then 70 divided by 3 is 23.33 degrees. So we've got gamma. And now finally, we just use this equation and calculate the theta 4s. So theta 4 initial we specified is 55 degrees. So now we just need to calculate those other two theta 4s. So 55 plus 6.67 is 61.67. And then 55 plus 23.3 is 78.33 degrees. So now we've got all of the points to match. So point 1 is initial, point 2 is middle, and point 3 is final. So now step 3 is to write Freudenstein's equations. This is Freudenstein's equation. So we need to write it 3 times, once for each point. The little t subscript would mean the point. So 1, 2, or 3. So let's fill that out. So we've got those 3 Freudenstein's equations, and then we need to put them into matrix form so that we can solve for the k's. So matrix form is going to have coefficients in one matrix, k's in the other matrix. So we'll have k1, k2, k3. And then we'll have what's on the other side of the equation goes in the last matrix. So the first matrix on the left side is 3 by 3. And the other ones are 3 by 1. So here I'm going to use variables. So this is theta 2 initial minus theta 4 initial. This is theta 2 final minus theta 4 middle. And this one is theta 2 final minus theta 4 final. So 3 is final, 2 is middle, 1 is initial. Okay, so I'm going to use those actual variables instead of the numbers so that you'll be able to apply this formula to other number situations. So the first, we'll just list those in order. So cosine of theta 2 initial minus theta 4 initial. And then what goes in this other matrix is the coefficients of every k. So for the first equation, actually in the second and the third, K3 doesn't really have a coefficient. This coefficient's just 1. So each column up here corresponds to K1, K2, K3. And each row corresponds to 1, 2, 3 initial, middle, and final equations. So K3 just has a coefficient of 1 for everything. So we'll just fill that out pretty easily. 1, 1, 1. Now K1, we need to grab the coefficients. So from the first equation, negative cosine 60, but 60 is actually theta 2 initial. So let's write that in. And then similarly for the other ones, theta 2 middle and theta 2 final. And then the K2 is going to be related to the theta 4. So that's a positive, and then we'll just have cosine of theta 4 initial, middle, and final. So now we've got these, and the next step is to solve. So we can do that if we follow the format A, K equals B, then K equals A inverse of B. So if we do that, then using the actual numbers, we get K1, K2, K3 equals 2.45, 8.54, negative 2.68. So these are our K values. And then the last thing we need to do is choose a value for the ground link and then solve for the lengths of the other two links. So these down here are the K equations. So we can solve K1 equation for R4. First, let's choose an R1, say R1 equals 10. So if we solve K1 for R4, then we'll get R4 equals 4.09. And then we need to solve the second one for R2. R2 equals 1.17. And then finally, we can solve this last one for R3. R3 equals 11.99. And units don't matter here because this is scale invariant. So now let's look at the simulation. So you can see here as it moves. And then here, this shows the actual points matched. So desired is the blue, actual is the red. So you can see that it matches at those specific points, but not necessarily on the rest of it. We can kind of zoom in here and notice that, so theta 2 is on the x-axis, theta 4 is on the y-axis. So these points here, you can see theta 2, initial, middle, and final. So we've got the 60 degrees. So this is 60 degrees here for theta 2 and 55 degrees for theta 4. Then this one is 80 degrees for theta 2 and 61 for theta 4. And then finally, we have 130 degrees for theta 2 and 78 degrees for theta 4. So you can see that the function matches at these specific points, although above it and below it, it's not real close. And you can also see here it outputs K values and R values. Now, if R ever comes out to be negative, then you can't actually build a linkage like that. It has there's no physical reality that would correspond to it. So then you'd probably want to repick your function or your points and try this again. So it's kind of a trial and error thing of how to get it right.